Okay, let's get started. Let's first review what we learned last week. Okay, last week we learned some basics of PCM, right? Pulse code modulation. Also, we discussed the delta modulation, right? And what you need to remember is the basic reason and fundamental reason why we need a PCM. Okay, PCM is simply one of the pulse modulation, right? Like a PAM, PWM, or PPM. Those are all pulse modulation. And pulse modulation, all of those pulse modulation use the pulse train as a carrier. Right? Same here, PCM also use pulses. However, the difference is, as you can see here in the name, it is like a coding. It's a pulse code modulation, right? There is some kind of coding concept. And the reason that we also need this kind of PCM is to like imitate, right? To work as a non-uniform quantization, right? We know that there are some problems in uniform quantization, right? Uniform quantizer is easy to make in hardware, but depending on the input signal, uniform quantizer have some problem. We discussed two different problems, right? First one is every quantizer has a limited input range. For example, -2 volt to 2 volts. When you have such a range, -2 to 2, but if the input is unexpectedly very high or very low, and it's beyond your range, then that value will be saturated. If you get a 3 volts, it'll be saturated to 2 volts. And at the receiver, there's no way to detect, no way to recover the original 3 volts because you lost already the information. So that's one problem when the input signal is too high. Second problem is the input signal is too low and your uniform quantizer always have a certain step size. This is input range for this particular step. So if your input value is between these two values, let's say this is 1 volt, this is 2 volt, just the example, right? If your input is between these, like 1.2, 1.5, 1.7 volts, things like that, then the output will be always this value. Output is always same. So if your signal is always like a small signal like this, that's the input signal you have, your output will be always constant. Why? Because this signal is too small and that disappears because of the quantization error. This is all because of quantization error. If you have a step size big, you have a more quantization error, right? So because of that quantization error, the second problem is that we lost everything in this case. So because of these two problems of uniform quantization, sometimes for particular signals, like most of the time you have very tiny signal and sometimes you have a very big. This kind of signal, we need non-uniform quantizer. But this is very difficult to make in hardware. So therefore, for this kind of signal, you want to put it into the PCM first. And inside there, you are doing coding. And after this PCM, the output is going to be like this small signal, small amplitude signal will be amplified, will be make it a little bit bigger. And the big input is almost the same as a big, like this, right? That's the output signal of a PCM. It's like a coding. You have some information or some signal, and after this coding, you are converting to another type of signal. But it actually has the same information, just your representation of a signal is now a little bit different. You are representing a little bit different way. Once you do that, then earlier the range of this is like only 0.1 volt. Okay, very tiny signal. But after the PCM, the range here now becomes like 1 volt, for example, right? So it is, if you have this kind of quantizer, now the earlier the input is like this, only tiny range. Now after this PCM, it becomes like this. So we have a more range at the input. Okay, so that's what we want to do in the PCM. This is an equation for PCM, and this input, this equation is just simple equation for input-output relationship. M is the input, V is the output, right? So whatever input you have, put it here, and this is the output you're going to have. And the relationship between input-output is simply a log function. Why do we have log function? This equation looks like a little bit complex, right? But what you want to remember is, anyway, A law, mu law, whatever it is just a log function. Different type of log, but log function. And when you look at this input-output relationship in a graphical way, like this, if you look at it visually, this is input, that's the output, and this is a log function. This is like x and y. Y is the output, x is input, and this is like a log function. Okay. And when you see this log function, input-output mapping function, now you can see that the input, when input is small, then your output is going to be like this range. So it's like amplification, 3 or 4 times bigger. When your input is already big, your output is almost the same, right? So that's why we need this kind of log function. This is mu law, this is A law, like the American standard, this is European standard, but both of them, anyway, it's a log function. It's a little bit different log function, but still what you want to do is the same thing. Okay? Small signal, small input, make it bigger, a large input, almost same. Okay? That's what we want to do in PCM. We also looked at the delta modulation. And in this delta modulation, again, the input is your analog signal. And your output is supposed to be a digital output, like a 0 or 1. And in this delta modulation, how to do that is you are trying to find the delta value. And delta is the current sample, the nth sample from the input signal minus the n-1th sample of the quantized output. So what that means is on the n-1th sample, you already make a decision, like this one, for example. Suppose that we already have a decision. Now on the next sample, what you want to do is you look at the input signal. And if your input signal is somewhere here, let's say, and this is higher than your previous input, that means your input signal is going up. Because the later sample is higher than the previous sample, right? So it's going up. The signal is going up. Your input signal is going up. In that case, this is like a positive. When this becomes positive, this is like a delta. And this delta becomes positive. Put that into the signal function. The output of the signal function is always +1 or -1. But this is a positive value. So this is +1. Now put this as a +1 here. Then you get this output. That's your output. What's the difference between this and this? Difference is this is mt, this is m sub qt. What's the difference? mt is your input signal. mqt is quantized output of that signal. Q means quantized, right? So let's look at that in the picture. Let's say in this picture, now let's see that this is n-1. Right here, let's say it's n-1. Just the example, right? This particular value here, that's m, q, n-1. Okay? This value. Now for the next value, for n, this is n, n. And what you want to do is we're going to look at this one. Let me skip the TS because TS is just the sample duration, so we can just skip the TS. This is nth sample. When you look at the input signal, which is the smooth curve, we're taking the n here. So this is input curve. This is input curve like this. Now the n position is right here. Actually, let me do it again. I think I got wrong sample. Let me see. Let me have this sample. So here is n minus 1. And this one is n. Okay. Now the right here, this value is m q n minus 1. This is nth sample. And what is m n? This mn is this one. This one, right? Here is the mn, right? What you are trying to do is you're going to compare this value, the red dot, with the previous mq n minus 1. You just compare. How do you compare? E equals to m n minus mq n minus 1, right? That's what you're doing on the first line, right? So this one minus this. Later sample, the next sample minus previous sample. In this case, this is lower than this. So E is going to be some minus value. Some minus. Negative value. So when you put the negative value, eventually put this negative value into the signal function, you're going to get the minus 1, right? So what's going to be the output? Eventually, mqn is equals to mqn minus 1 minus 1. So what does that mean? Now this one is mqn minus 1. mqn is mqn minus 1 minus 1. So this is mqn minus 1. So we are going to do minus 1 from here. So here, that is mqn minus 1, n. Right? So you are looking at the stair step function. That's mq. That's the signal, output signal after quantization. The smooth curve is your input signal, mt. So you see the difference, right? This red one is mn. The black one here is mqn. Okay? So that's difference. Same thing for all the other samples. That's the idea. And once you do that, always you're going to get plus 1, minus 1, plus 1, minus 1, something like this, right? So every time when you get plus 1, you get 1 as the output. Every time you get minus 1, you get 0 as output, right? In that case, let's look at here. 1, because you go up, go down, 0. Go up, 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 1, 1, 1, 1. Go down, going up, 0, 1, something like this, right? That's what you get here as output. That's the output, bit sequence. That's the output. So input like this, mt goes into the delta modulation. The output is this sequence, 1, 0, 1, 1. That's your output of delta modulation. Okay? Simply, that's it. Okay, so that's what we discussed last week. Let's look at the block diagram of delta modulation. So right here you see the delta modulation, delta demodulation. This is what we just discussed in the delta modulation. In this is delta demodulation, which is the receiver. But at the receiver, you need to have an accumulator. Right? You need to have accumulator. Why? Because when you have 1, 0, 1, 1 comes in into the sequence, you are getting like going up, going down, going up, 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 up. The next sample is going to be on top of the previous sample. Every time when you get a new sample, you're gonna accumulate. Only then you're gonna get these kind of signal, right? So that's why you need to have an accumulator here. This is gonna be 1, 0, 1, 0, 0, 1, 1 kind of thing. After decoder, you're gonna get +1, -1, and then you're gonna do accumulation. Eventually, after you do accumulation, right here, you're gonna get this signal, right? This kind of output is what you get here. After that, we need to go through the low pass filter because we want to get this function, this output, right? Smoothing. We are trying to do smoothing. After that, we are reconstructing the original smoothing signal, right? So that's the whole story. We need to think about these kind of conditions when you do delta modulation. Now think about that. When you do delta modulation, sometimes you see these two different distortions. One is slope overload. Your slope is too fast. Your slope is too steep. Too steep. So the delta modulator is trying to catch up, but this is the fast you can do, right? But the input signal is too quickly going up, so we have this much of error. These shaded region, gray region is the error. Second error case is that your input is almost constant, but still your delta modulation can only do +1 or -1. Okay, delta modulation cannot do like stay. There's nothing like stay. You have to go up and down, up and down. So in this case, you have to go up and down, up and down. Every time when you do that, you have some error like this. That's the granular noise. We have these two, distortion or noise. Every time when you see this kind of noise, or you have a severe distortion, now you have to think about two things. Why do we have this problem? And how can you avoid the slope overload? The reason we have this problem is because, what is this one? Typically step size is this one. That's the step size. This one is sample duration. You're doing sampling, right? This is time domain. So you are doing sampling. So this one is a sample duration. After you do sampling, you have a sample duration. So that sample duration is too large. In other words, sampling frequency is too low. That's the problem. Okay, sampling frequency is too low. So how can you avoid this problem then? You want to make your sampling frequency faster. Okay, faster. Let's say let's change the sampling frequency. Okay, we want to make a faster, higher sampling frequency. If you have a higher sampling frequency, what happens? You're moving. Step size is the same. Okay, I want to make a same step size. Make it faster. Because our sample duration is going to be shorter, right? Because we have a fast sampling clock, sampling frequency. It's faster, right? So this problem is much reduced. So that's what we need to do. Faster sampling. Okay? So if this problem happens, which means your sampling frequency is too low, too slow, okay? What about this one? How can you remove this granular noise? How can you reduce it? You cannot remove it, but you can reduce it. How can you reduce the granular noise? You can make a step size smaller. Like right now, this is a step size, but you can make small step size like that, right? If you have that, then let's make a small step size. It's gonna be like this, right? Because your step size is smaller. So your error is only this much. So you can reduce the error, granular noise. So putting together, what you need to do is you have to make your sampling fast enough. You need a faster sampling clock. You also need small step size. Okay, that's the best way you can do. Now the problem is, what's the problem? Fast sampling clock. We know fast sampling clock is always good. We also know the step size is small is always good. Why? Step size is big means you have a lot of quantization error, right? That's not good, right? Quantization error needs to be small. To do that, you can make a step size small. What's the problem of small step size and fast sampling clock? Very expensive. Very expensive, right? So that's a problem. That's a problem. So if you use the very expensive A to D converter, we don't have to worry about these things, because expensive one have a very fast clock, sampling clock, very small step size, many step sizes, so no problem. But expensive. Okay, so remember those things. Okay. There's also delta sigma modulation. It is almost same as a delta modulation. The difference is that in the delta modulation, transmitter is just calculating the delta and change it to 0, 1, 0, 1. Receiver will use accumulator and put them together and reconstruct the signal. In delta sigma modulation, is almost the same, but only difference is that you have a sigma at the transmitter. So in this case, you have an accumulator at the transmitter. In previous delta modulation, accumulator is in receiver. In this case, transmitter. That's only difference. Everything else is the same. So let me just go to the next topic. Okay, this slide is kind of review of what we learned in the previous semester. We already learned the noise in analog system, right? We already learned this one. Okay, so let me review a little bit about the noise in analog communication. This is what we learned last semester already. Okay, I just want to remind you what it is. Here, what is ST? We always use ST for the transmitted signal. Okay, we have a transmitter. And eventually, after do modulation, the transmitter will transmit the signal over the air. Right? Your signal is going over the air. That's ST. Right? You have a TX. Let me read it here. We have a TX. Eventually, you're going to get some information, message. That message go into the transmitter. Eventually, after the modulation, inside here, we do modulation. And then through the antenna, we are transmitting over the air. That's ST. That's ST, right? We also have a receiver. Main thing that we are going to do at the receiver is demodulation. After demodulation, we are trying to recover original message back, right? We are trying to recover the message back. But this message, hopefully this message is same as the original one. In that case, there's no error. But that's our hope. It's not always. It is almost the same, not exactly the same, but almost similar to our MT. So that's why I put it hat. Okay, M hat T, almost the same. But there can be error, right? In between here, we have a channel. And what do we have in the channel? We have noise. Right? So noise that we are looking at is additive noise. Remember this word, additive noise? Additive noise, right? Additive. This is actually very important. We discussed this one, right? Some of you, heard my lecture last semester. What we do is we are talking about additive, white, Gaussian noise, right? So we call it as AWGN. Remember this word? Each one has a meaning, right? Why is white? Why not yellow, blue noise, red noise? And there are many colors, right? So why especially, why white? Why not yellow? We discussed that, right? So some of you remember why? Why white? Why white?
Same the ingredients of noise.
Say it again.
Same the ingredients of noise.
Same ingredient of noise. Okay. Any other? Anyone else? Okay, this is important. I think we discussed this one several times, right? Okay, let me remind you one more time. We are always looking at AWGN noise. Okay? We are not looking at any other noise. There are many different type of noise actually, but we are not looking at other noise. We are only looking at AWGN. Right? Let's take a look at one by one. Noise, just noise. We know that. What is additive noise? Noise is being added. Okay? Noise is added. We are not, some of the noise is like this one, multiplicative noise, but we are not looking at those things, right? We are only looking at additive noise. So noise is being added. So that's why, what is the receive signal? RT. Receive signal RT is transmitted signal plus noise, additive noise. Additive noise. That's what we have here. Additive noise, right? Noise is added. So that's why we call it as additive. What is a Gaussian? Gaussian is a distribution. Distribution of what? Distribution of noise amplitude. Noise amplitude, right? Let's say this is a 0. Think about circuit. We have some microprocessor and we have another chip. Let's say motor control. Between here we have some connection. You know that there's a noise in here, right? Everywhere you have a noise. Everywhere. Let's say if there's nothing, there's no noise. In this case, you always get 0 volt because we are not doing anything. But because there's a noise, what we see is that when you measure it here, you see some volt. Something like this, right? That's noise. That's noise. Every time when you do communication, when you do these things, everywhere you see noise. And noise is always looks like this in time domain. This is time domain. Now what I'm trying to do is I like to measure the amplitude of the noise. In this case, amplitude is like a 0.1 minus 0.5, something, right? Every time you have a different amplitude. This is a little bit big, so maybe 0.5, right? Every time you have a different noise, sometimes positive, sometimes negative, big, large, small, something like this, right? Every time. And collect all this amplitude, put them together, and let's make a histogram. When you draw the histogram, let's say this is 0. Sometimes the amplitude is 0. Sometimes you have a very large amplitude. like a 0.5, sometimes small. So when you put the amplitude as a histogram, you're going to get these kind of distribution. Most of the time, with the highest probability, the actual noise amplitude is almost 0. And with a very low probability, it's not common. It happens only once in a while. You get large peak, like a large amplitude, 0.5, maybe here is 0.5, something like that. But this one is not common. Only happen like once in a while, but most of the time it's small, somewhere here. So that's your distribution of your amplitude of the noise. So this one tells you what amplitude your noise is. Okay, this is the amplitude of the noise. Is there any other distribution? Of course, there are many distributions in the noise. There is this is not all the noise. There's a Laplacian distribution. There are many other noises with many other distribution. But we are looking at the simplest one. This is the simplest one, and this is the easiest one. That's why we are only looking at this one. There are many different types of noise. So this one tells you the distribution of your amplitude of the noise. Okay, remember that. Why we call the Gaussian? Amplitude is Gaussian. This is important. This is the most difficult one. Why do we call white for our noise? Okay, something weird, right? Why do we put the color in noise? There's nothing in the color, right? The reason that we call this noise as white is because that when you look at the white color is let's say white. You know, when you look at the this monitor, you know that monitor is using RGB, right? Red, green, blue. So every color you see in this monitor is created by RGB. This is RGB cable. You are getting only RGB signal, right? You're only getting RGB. How do you make white color? You are getting RGB mixing together. You are gonna get white color, sometimes green color, black color, white, every color, right? So white color is a very special color in such a way that white color is a mixture of all different colors with the same amount of amplitude, same amount of color, okay? In the frequency domain, this is like a frequency domain. In frequency domain, you know the rainbow color, right? Red, green, violet, all these different colors have a different frequency. You know that? Every different color has a different frequency. This is like a blue. This is like a violet. And there's a red, green, yellow, things like that, right? So different colors, different frequency. And how do you make white color? All these different colors, put it all together with the same amplitude. Blue, you have this amount of blue. You have the same amount of violet color. You have same amount of R, G, all these different color. Only then you get a white color. In this case also, right? How do you make a white color using RGB? R, you get this amount. Same thing, right? When you get same amount of full value, you get white. What if you have a little bit smaller? Let's say this. In that case, maybe it's a little bit purplish white color, right? It's not true white. So true white is only when you have same amount for every different frequency, all the frequency. That's white. So why are we talking about these things in noise? Our noise is very special noise such that when you look at this noise in the frequency domain, okay? When you look at the noise, our noise in the frequency domain, our noise has this energy, this much of energy. Our noise has all of the different frequencies with the same amount of power. Flat, basically. In frequency domain, it's flat. That's our white noise, right? That's our noise. This is a power spectral density. All the different frequencies have the same power, equal power for all of the frequency. So that's the condition of white. This is called white. Not color. We are not talking about color. We are talking about frequencies. All the frequencies have the same amount of power. Okay? So that means white. So in the frequency, if we have all flat power, what happened in the time domain? Impulse in time, yes. Flat in frequency. Let's take a inverse Fourier transform. In time domain, you are going to get impulse, right? Just take a inverse Fourier transform. We're going to get impulse. This in frequency domain, we call it as a power spectral density. This is power spectral density, meaning how much power is allocated for each frequency. That's a power spectral density. Now let's take an inverse Fourier transform. We get this one in time. What do you call this? What is this in time? This is called autocorrelation. Correlation function, correlation. Actually, it's autocorrelation, but it's a correlation. It's autocorrelation, basically. So when you have this kind of autocorrelation, you heard about autocorrelation, right? What does that mean? Autocorrelation is impulse. That basically means is, what is autocorrelation? Let's say I have this signal, ST. I want to calculate the autocorrelation. How can you calculate the autocorrelation? You have your own signal, and you are making another copy, same signal, and slide it. And you measure the energy, overlap the energy. So that's how you calculate it. Let's do that. So make another copy. And now it's the same thing. You are going to slide it, like slide it, like slide. So first, when you have a little bit of overlap like this, you have a little bit of energy. So when you have a little bit of overlap, you have a little bit of value. Now you shift it a little bit more. It's going to the right. You have a more overlap, you're going to get more value. If you have a perfectly overlap, you get maximum value. When you slide and keep going, and you are moving out, again, you have a little overlap, so going down again. So typically, autocorrelation function is like this, going up, going down. But in this case, there's nothing like going up or going down. Zero always, suddenly it goes jump, and then again back to zero. So that's very special way of autocorrelation. What does that mean? Autocorrelation of delta function basically means that this signal, let's say this signal has this autocorrelation. That means this signal is sliding and trying to calculate autocorrelation, and this signal is a little bit mismatch in time. I'm just trying to correlate, right? Trying to shift it, but it's not exactly same, but a little bit off in time, little bit off. In that case, correlation is 0, because here is a 0, right? This x is like, this is t, but actually this is delta. What is delta? The time difference is delta. Okay? So when delta is 0, only then you get some value. Otherwise, you get 0. So if your signal is a little bit time mismatch, your correlation is 0. Only when you have a perfect match in time, meaning delta is 0. Let's say you have a perfect match, exact perfect match. In that case, perfectly match, so delta equal to 0. Only then you have some peak value. Do you see what I'm saying? It's a sliding, right? It's sliding. So when you slide, initially you have a time difference. The time is not mismatch. So in that case, the correlation is 0. Correlation is between these two is 0. And still 0, 0, 0, 0. And if you have a perfect match, you get some value. And again, you have a 0. That's our noise. Sounds difficult, right? Sounds hard. What does that mean? That basically means is our noise is like this. This is our noise again. Our noise is like if you have a little bit of time mismatch, correlation is 0. That's what this means. Okay? No correlation, nothing. If you have a little bit of mismatch. Only when you have a perfect mismatch. Perfect mismatch means you are this sample is multiplied with its own, okay, its own sample. Only then we have some value. So this is our noise, and our noise has this, something like this. This sample, that's one noise sample. And the next sample, what's the correlation? 0. Okay? This sample, just the previous sample, what's the correlation? 0. Every time, this is noise, right? Every time you look at the different sample, this sample, of course 0. But this sample and the very next sample here, still correlation 0. When do we have a correlation? This sample and this sample itself. Only then you have correlation. That's our noise. Okay? Simply speaking, our noise has no correlation. That's what white means, eventually. White means flat in frequency domain. Okay, that's what white means. But when you have a flat in frequency, we have this kind of autocorrelation in time. When you have this time autocorrelation function, that means we have 0 correlation in noise. What does that mean? That basically means it's like this, right? Let's measure the noise. At some point, you measure the noise is 1 volt. At some point, right? My noise is 1 volt. What is going to be the next noise? We never know. This time, noise is 1 volt. On the very next sample, of course, you also have a noise, right? And can you expect the noise on the next sample? You cannot expect because this is completely random, no correlation. If there's a correlation, let's say there's a correlation. In that case, this is 1 volt and there's a correlation. So next sample is maybe a little bit close to this, maybe 0.8 or something. If there's a correlation. Correlation means it's close, right? Similar. That's correlation. If there's a correlation, we can expect what the next sample is going to be. But in this case, no correlation. So it's completely random. Completely random. Every sample is completely random. 0 correlation. It's a very important. Okay. So that's the word of AWGN. Okay, so coming back here, this is AWGN. W is AWGN. So this is the additive noise. What is the main thing that we need to consider in when you have a noise. When you have a noise like this, right? We have noise, then we are going to receive transmitted signal plus noise. And what is our mission? My goal is to recover original message. But problem is there's a noise together. So question is, how can you recover message from RT? RT is what we receive. There's noise. How can you do that? So that's the question. What is the important metric? When you have a noise, we use metric, one of the metric. This slide talk about some details about AWGN noise. Okay, we already discussed AWGN, but look at here. What is SWF? This is a power spectral density, PSD. And what is the power spectrum density of AWGN? Flat, just flat in frequency. Power spectral density is in the frequency domain. So this power spectral density is a frequency domain, and frequency domain in the power spectral density of AWGN is flat. And n naught over 2 is the value. You have, this is frequency, flat, and the value of this is n naught over 2. So this one means this in graph. When you have this one, this kind of power spectral density in the frequency, now let's take an inverse Fourier transform. You're going to get this autocorrelation function in time domain. This one is delta, right? Delta function. So that's autocorrelation function. So simply this is the equation. Okay, that's it. That's it for AWGN. So it's important to remember. Not many people understand this one, to be honest. So I just want you to remember the white. Okay? Why do we call this white? Okay, let's move on here. Every time when you have a noise like this, right? We have a noise, but we want to recover the message. The important metric is SNR. We always have to remember signal to noise ratio. What is the signal to noise ratio? We have a signal. We also have a noise. Someone is sending cutoff. We have a signal and we have a noise added on top of that. And signal has its own power. Noise has its own power. And the problem is our received signal, RT, is signal plus noise. And put them together and we cannot differentiate, okay? Because it's all mixed already. But what we can do is we can measure the power. We can measure signal power. Also, you can measure noise power and put it as a ratio. That's signal to noise ratio. So here you see that, what is this one? Expectation of S squared. S is transmitted power. Let's do square. What do you get? When you put the square, you're going to get power or energy. Okay? Each ST is like some signal on time, right? When you put the square of that, you are going to get energy or power. Now let's take expectation. What is expectation? Expectation is like integral. Something like that, right? Integral of your S squared t, dt, something like that. What do you get if you take expectation? You're going to get average. So what does this mean? Average signal power. You're taking average over time. You are measuring for a long time and just getting average. So this is average signal power. Same thing for this one, right? You're going to calculate the average noise power. So average signal power divided by average noise power will give you signal to noise ratio. This simply means that I have this much of signal power and you have this much of noise power together in this received signal. I have this amount of signal power. I have this amount of noise power, right? And I'm going to put that as a ratio. Typically, SNR is, that's called SNR. SNR is high, large value. What does that mean? If SNR is high, this is much bigger. Signal power is much bigger, relatively. This is relative, right? Because this is a ratio. We don't care what is actual value, what is actual power. We don't care. What we care is ratio. Okay? If the signal power is relatively larger than noise power, that means signal to noise ratio is high. That's good. Why is that? Look at your signal and noise are all mixed together. And noise has a much higher power than signal. In that case, we can recover the message easily. Think about a simple scenario. I'm talking to him. Okay, I like to talk to him. My voice is signal. Okay, right here is very quiet, so noise is pretty low. So SNR is very high in this case. Okay, now suddenly these guys are making a lot of noise. It's too noisy. In that case, when I talk to him, he cannot listen. He does not understand because there is so much noise, right? If there is so much noise power is increased. Okay? In that case, SNR is low. If you have SNR is low, very difficult to recover because your message needs to be recovered from signal, right? Noise has no information. We have to recover this from signal. So therefore, S signal has to be large, simply, right? So SNR is the very important metric especially when you have noise. And in communication, we always have noise. If there's no noise, then it's not communication. It is just a signal processing. You learn the signals and systems, right? Convolution and all those things. In that scenario, there was no noise. In communication, now you are learning noise. So you should have a noise in communication. Okay, so that's a communication scenario. Okay, here, all of these things is just review of analog communication. Now we are gonna again review the analog communication system here. What is ST here in this case? This is the case of transmitted signal in general. Just AC, this is the amplitude, the maximum amplitude, and cosine, FC is a carrier frequency, right? And theta, we call that as a phase. So this is just a general waveform for transmitted signal. What we are trying to do is we want to simply calculate average signal power. And how can you do that is we know that this signal cosine is a periodic function. It's like periodic, right? And we know the period, t. T is the period of the periodic function. Periodic function always has a period. That period, we call that as a t. And you know that in periodic function, what is the easiest way to calculate the average power? Easiest way is periodic function is like repeated, same thing, repeat again. So you are taking only one period and calculate the average. That's it, right? For average, for periodic signal. So that's why we are taking only 0 to t, only one period. And square, we need to do square. Don't forget the square, very important to do a square because what we are doing is power, signal power. This is a power ratio. Signal power divided by noise power. It's a power ratio, okay? Not just ratio, power ratio. So we always have to do square. So this is a ST, you do square, and then integrate over one period. And this is the size of the period because we are taking average over that time. So 1 over t integrating from 0 to t, square of that. That's very simple. Simple equation. That's how you calculate the average power, signal power. Now let's take a look at this square. I think last semester I told you that this one is very easy to remember, right? I would suggest you to remember this. Of course, you can calculate. I know that, right? This is like high school mathematics. We already know, but it's very easy to remember. So it's better to remember. What I want you to remember is this AC is a constant value. So we have an AC square. So bring AC square out like that. Okay, like that. So what is remaining is cosine square. So let's take a look at cosine square. Cosine square x is what? Using the identity, what is this? 1 plus 2, I forgot that, 2 cosine, no, no, this is not like this. This is like something like this, right? This is the one, right? Yeah. So you can change this one square into this one using the identity. And what you can see here is when you do square, x now becomes 2x. That's one thing. Also, we have only cosine square, only one term, but now we have two terms. And especially first one is going to be constant. So let's do the same thing. Cosine square here. Now when you change it to that, 1 over 2 goes out here because that's constant. 1 plus cosine 2x is right here. Okay? This is x. So 2x is this one, right? We still have the integration. Now let's take integration. Constant integration, nothing. Okay, just multiplying t here. Make it separate. So from here, integration of 1, we get t. What about this one? Integration of 0 to t to cosine 2x. We're going to get 0. You know why, right? Why is that? Cosine, let's draw the cosine x. This is cosine x. What is the cosine 2x? We have a 2 cosine inside. The period is 1 over 2, right? So cosine 2x. What's the average? 0. Because we have a positive, negative, positive, negative, positive, cancels out. So this one always going to be 0. So what is left over is what? T. That's the only thing you're going to have. So t cancel out. You're going to get this. So now what I want to suggest to you is to remember integration of cosine square x, not x, something d cosine 2 pi f c t plus theta square 0 to t dt. What's going to be? What's the value? Same thing, right? We have a 1 over 2. You're going to have 1 over 2. And the cosine 2x will be 0 anyway. This will be gone anyway. We know that. It's already gone. You only have a 1. Integration t. So that's going to be your value. Okay, always. So every time you get this, you always get this. That's just simple way to do it, right? So that's what you're going to get all the time. So that's the average signal power. This is how to calculate the average signal power. Now, we also need to calculate the noise power. How do you calculate the noise power? This is also very easy, actually, but I'd like to tell you a little bit of background. Coming back here. In this slide, let's go back to one more slide. When I talk about the noise, it was W. That's noise. That's also what I have as W. That's noise. But in the next slide, I'm talking about N. This is noise. ST is the same. ST here, ST there, same thing. But here, when I say noise, is NT. Previous slide, I make it as a WT. So did I make a mistake? Did I use two different symbols for the same thing? That's a mistake. No, right? Then what's the difference between WT and NT? I told you this one, right? Last semester. Remember, some of you? Kwon-hyuk-chan? What is that? You were in my last semester, right? What's the difference? Oh, you didn't take it? Oh, sorry about that. Okay. I saw you many times, so I thought, yeah. Okay, Choi-Byung-chan? I know you take my semester. What's the difference between W2 and T? A little bit more specifically. Okay, let's take a look at the details inside here. I'd like to draw a little bit more detail about receiver. Okay, inside the receiver, what is the first thing you have in the receiver? First thing you have is a receiver. The noise, the filter. Okay, you have a filter. That's the first thing you have. We call that as a band rejection filter. And later then we have some demodulation, and that's a receiver, right? The difference between WT and NT is that when you look at the noise in the channel, that's WT. That's the true noise in the air. Noise in the air is WT. Noise right here is NT. We still have a noise, but in a different position. Why do we care about NT and WT? Why do we make it differentiate? Because WT is the noise at the channel, NT is the noise in the receiver. That is different. Because of the filter. Okay, we have a filter. What is this filter? It's not low pass filter. It is a band pass filter. Okay, band pass. In the frequency, you know the frequency. In the frequency, we have a carrier frequency. Your cell phone is using 1.8 gigahertz, right? But in the air, there are so many different frequencies. But our cell phone is using only 1.8. So first thing to do in the cell phone is that you have a filter, and this filter filters out all the other filters. Only it passes 1.8 gigahertz, because that's what we need. That's what you have in the filter. So simply speaking, what is the power spectral density of our noise? As I said earlier, flat. That's our power spectral density of our noise. This is our power spectral density, which is flat for all frequencies. But that's the power spectral density of WT. Now we have a filter inside the receiver. This is the band pass filter. So put this noise into bandpass filter, and you're going to get the output. What's the output power spectral density look like? Let's say this is WT, and when you have a filter, your filter has a certain bandwidth, bandpass. And put this signal, put this noise into here in the filter, the output is going to be like this. So your noise NT has this spectral density. This is power spectral density of NT. And this one is your bandwidth of the noise. Okay? This is the bandwidth of the noise. It's typically this is called right here is called B, 2BT. Okay, that's what we call. So that's why this noise power spectrum, this one noise power N is simply what is the bandwidth? It's a 2BT. What is the noise power? That's N0 over 2. That's what we have here, right? N0 over 2. So simply, this is a power. So 2 N0 over 2 times 2 BT, that's going to be N0 BT. That's this one. So that's a noise power. Simple, like that. That's noise power. 네 시까지인가요? 4시? Okay, let's continue next week.